It is a pleasure to welcome you to the 5th edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Biogeotechnics was hosted in 2024 during the 5th edition of the AGERP lecture series. The following lecture on Geomechanics for Geothermal Applications with special reference to Microstructural Insights on Thermal Damage and Hydraulic Fracture Mechanisms was delivered by Dr. Pabasara Kumari at this workshop. Dr. Pabasara Kumari is a lecturer in geotechnical engineering at the School of Civil Mining, Environmental and Architecture Engineering of the University of Wollongong. She received her PhD from Monash University, Australia in 2018. Her research interests include geomechanics applications for deep and shallow geothermal extraction, reservoir stimulation and waste utilization for geotechnical engineering applications. She is a recipient of the prestige 2024 Discovery Early Career Research Award from the Australian Research Council, which supports her current research focus on investigating geothermal heat recovery and energy storage from underground mines. She was also nominated as a 2024 American Rock Mechanics Association Future Leader.
Thank you very much for this opportunity. Thank you very much, Professor Das, and the opportunity given by Partha, my colleague, and Satyam. In today's presentation, I will be talking a relatively new topic, perhaps geomechanics for geothermal applications, and I will be focusing more in microstructural insights. In this presentation, I will provide a brief introduction to geothermal energy and geothermal resource potential for both Australia as well as India, in case this is a new area for you. And most importantly, why we need to conduct geomechanics research in this unique new discipline. And then I will go through a few selected research topics as examples, like thermomechanical behavior of reservoir rocks and reservoir stimulation, like improving the permeability of these reservoirs, and how microstructural analysis can be incorporated into these type of problems, and then the importance of that. As Professor Das highlighted, I received my BSc from University of Wollongong, Sri Lanka, so I'm also a close neighbor for you, and I did my PhD at Monash University. I specifically want to acknowledge the research training and experience I received from Monash University's 3GD research group, particularly the support from my PhD advisor, Professor Anjit Pathegama. I'm working as a lecturer at University of Wollongong. It's a beautiful coastal city located in south of Sydney, and you all are welcome to visit us. And as Partha highlighted earlier, I just received very good news regarding 2025 fellowship in the Australia-India Women Research Exchange Program. So next year I have opportunity to visit India and collaborate with the Indian Institute. I specifically planning to come to Indian Institute of Science, Bangalore, under this program. Okay, so moving on to the lecture. So what is geothermal energy? So geothermal energy is essentially heat or thermal energy in the Earth's crust, and it comes from formation of the Earth as well as the radioactive decay of minerals. And geothermal applications can range from geothermal-based electricity as well as various thermal applications. These are some photos from Iceland. I was fortunate to visit some of these sites. And Iceland produces most of the electricity from geothermal energy, and almost all of the heat is coming from geothermal energy. If you look at the map here, so you can see Iceland as well as our neighbor New Zealand, they are lies over volcanic hotspots, and also they possesses underground water reservoirs continuously recharged by rain. So this makes these systems very desirable for geothermal production. Most part of the Earth's crust get about 25 degrees Celsius hotter every kilometer you go down. We call this as geothermal gradient. But if you go down a kilometer below Iceland, you might hit more than 200 degrees in some places. This provides geothermal heat very close to the surface. And this image shows a geothermal-based electricity plant, and you can see these systems, still they use turbines to rotate an electricity generation, but unlike traditional fossil power plant, they don't need to burn coal or gas. Instead of that, they use hot water or steam to run the turbine. So that's the difference. But geothermal energy is not just electricity. There are various other applications. As this slide shows, apart from electricity generation, we can use geothermal energy from different applications, like space heating, recreational purposes, geothermal heat pumps, and many different industrial and agricultural purposes, depending on the temperature. And this is an image from geothermal pools located in Mornington Peninsula in Australia. And these types of shallow geothermal systems are generally considered as more accessible form of geothermal energy, and can be used for residential, commercial, and various industrial settings. So based on the example of Iceland, now I think it's clear near tectonic boundaries, volcanic areas, there are readily available accessible geothermal heat at shallow depths. So these are called conventional hydrothermal geothermal systems. They can be water dominant or vapor dominant systems based on the temperature and pressure. Technologies to utilize these types of systems are readily available, specifically for geothermal-based electricity. And almost all of current commercial geothermal production is based on these types of systems. However, when it comes to other parts of the world, the biggest challenge of geothermal technologies is to create optimal flow rates, because the technology relies on flow rate as well as temperature difference. And when it comes to deep reservoirs, we might need to create fractures artificially to enhance the fluid flow, which we call reservoir stimulation. And in recent years, researchers have proposed various different configurations, use of different types of fluids in order to increase thermal efficiency. And this is one such example. This is a closed loop configuration, which use carbon dioxide, which is a supercritical fluid under these high temperature, high pressure conditions. But these are very hypothetical proposed scenarios, I would say. When it comes to Australia, we can identify 3 different types of resource categories, considering the depth of the reservoir, which is an indication of approximate temperature, and then the amount of enhancement required to produce required flow rates. So these types of shallow geothermal resources are typically in the range of 500 meters to 1.5 kilometer, and they are mainly used for direct use applications. They don't have enough thermal energy for electricity production. And deep natural reservoirs that are greater than 1.5 kilometers can have substantial fluid flow. These are typically sedimentary fractured aquifers with the natural permeabilities. With some level of enhancement, this can be viable for either direct use or electrical generation. In Australia, deep crystalline formations, which are called hot dry rock reservoirs, have received a lot of interest in last 2 decades. But these types of systems require significant permeability enhancement in order to achieve economical flow rates. Here you can see various current and proposed locations in Australia for geothermal exploration. This slide summarizes how Australian geothermal resources could potentially be used depending on, here you can see the various depths and then the target temperature. So crystalline rock-based hot dry rock systems or hot sedimentary aquifers I mentioned earlier are the reservoirs considered for geothermal-based electricity. But as I mentioned earlier, significant permeability enhancement is needed in Australian context because we don't have volcanic-based systems like in Iceland or New Zealand. And in considering Australian continent, here you can see the map of temperature at 5 kilometer depth. So in Central Australia, Geoscience Australia has estimated there are locations which have beyond 200 degrees Celsius at around 5 kilometer depths. Several companies have attempted to explore these systems and had various variable success in last 2 decades. Shallow geothermal technologies like ground source heat exchangers coupled with ground source heat pumps for heating and cooling applications are gaining popularity in recent years in Australia. Another type of geothermal technology that I'm currently researching is mine-based geothermal systems, because there are deep underground mines in Australia that have reached quite higher temperatures, even beyond 40 degrees, and these systems can be viable sites for direct applications. And hydraulic conductivity of these systems are elevated due to artificial voids like mine galleries, mine shafts, fracturing, etc. So we can expect quite high water yield in these types of systems. So that's what my current Australian Research Council funded project is looking at, to identify these sites and looking at various configurations and methodologies to implement these types of technologies. When it comes to India, I included this slide because there would be some of you interested in what's the situation in India. India's geothermal potential is estimated approximately 10 gigawatts. However, this remains largely untapped. The Geological Survey of India has identified more than 340 hot springs with geothermal potential, and most of these locations have been surveyed. And this map shows various geothermal provinces, especially geothermal springs and fall systems which present opportunities. And you can see particularly areas in the Himalayan belt exhibit active heat reservoirs linked to magmatic systems and geological faults. But some of the challenges both countries face are high costs and lengthy timelines for exploration, the need for more comprehensive data when it comes to heat sources and fluid dynamics, and of course policy and investment support to overcome these kind of barriers. Next, I'm moving to the presentation regarding geomechanics research, why geomechanics research is essential in these types of fields. So when it comes to geothermal energy, geomechanics provides essential fundamental inputs in many areas. Preliminary, it's very important to understand the properties of subsurface rocks and their ability to store and transmit heat. We call reservoir characterization. And it's very important to understand the stresses and strains within the crust, because that affects reservoir stability as well as fracture propagation direction. As I mentioned earlier, when permeability is not sufficient, it's important to create fractures artificially. And it's important to ensure integrity of geothermal wells, prevent leakages, and maintain long-term fluid transport and thermal recovery. Therefore, the knowledge of coupled thermo, hydro, mechanical, and chemical mechanisms is very important when it comes to geothermal systems. And it's a very complex problem. And this sketch summarizes these processes and how they are interrelated. Some examples. For example, temperature, pressure, and chemical effects change fluid and rock properties. And temperature and pressure can also change hydraulic and chemical processes. They can change fracture pathways, cause mineral dissolution, precipitation, etc. So multi-physics coupling techniques are usually used to uncover these challenges. However, these types of simulations can be very computationally extensive and require significant computational resources. Also, when it comes to modeling these interactions of different physical processes, it's very challenging and require validation. Again, it requires advanced experiments, which can be challenging to design and perform. Another important aspect I want to highlight is the necessity to consider the scale effect, because today's presentation I'm highlighting the micro scale mechanisms mainly. But now here we need to consider the scale effect across these coupled processes. So we often use small scale laboratory experiments to understand fundamental mechanisms, and micro scale observations and analysis is quite important to understand the underlying mechanisms, such as pore areas, rock fragmentation, tortuosity in fluid flow through these pores and fractures. So these types of mechanisms are quite important to explain the experimental observations. And then we need large-scale advanced experiments which can connect these micro and meso-scale scenarios to field-scale observations. So this framework shows various techniques that can be used to capture these underlying physics to develop constitutive equations and apply that knowledge to understand coupled processes and interactions that can be applied in the field scale ultimately. Here you can see this 4-scale modeling that can capture this whole spectrum, which can be considered as a framework for future research. Next, I would like to briefly go through some of the research studies that I conducted. First, thermomechanical behavior of granite rocks. I mainly use granite for my PhD and following research, because in Australia we mainly targeted hot dry rock reservoirs, which are essentially crystalline rocks. So the thermomechanical behavior of these reservoir rocks are influenced by various factors like rock type, mineral composition, porosity, existing fractures, and environmental conditions like temperature, stresses, fluid saturation, etc. And here you can see some of the experimental results. So to conduct these advanced experiments, I was fortunate to use the custom-built high-pressure, high-temperature rock triaxial facility at Monash University, which can simulate deep reservoir conditions. And we use various granite types in this work. So here you can see the failure envelope. So we know traditionally rock failure in compression can occur in 2 main ways, dilatancy and failure by strain softening under relatively low confining pressures, and failure by strain hardening under elevated confining pressures. So this experiment shows how rock failure will alter with extreme confining pressures with the transitional regime at intermediate pressures. So we observed that specimens fail below 60 megapascal confined pressure, mainly fail by shear localization, and sample tested beyond 90 megapascal exhibited strain hardening characteristic despite they were brittle granite rocks. And temperature was another important factor when it comes to geothermal reservoir rocks. And based on the experimental results, we can see temperature can cause initial strength gain in these considered ranges following strength reduction beyond 200 degrees. And this critical temperature, the temperature that creates a reduction of strength, depends on the material as well as the stress condition. And we experimentally observed the failure is a non-linear scenario, and we tried to model that capturing temperature-dependent material properties as well. Here you can see geothermal effect of the heating and cooling or for mechanical behavior, because this is another important research question, because geothermal reservoirs often subjected to large temperature gradients because of injection of cold fluids into these hot reservoir rocks. So traditionally we use water in these types of systems. And here you can see we considered different heating and cooling scenarios to capture this situation. For example, we did experiments without cooling the samples under heated condition, as well as we quenched samples. In other words, we injected cold water into the heated rock to mimic the situation close to the well bore. And also, we also applied slow cooling rates to replicate natural cooling of surrounding rocks. In these experiments, we used this non-contact 3D optical deformation system, and it allows us to understand the axial and lateral deformations of the rocks. And here you can see variation of uniaxial compressive strain, Young's modulus, axial strain at failure, Poisson's ratio, etc., the basic properties and their behavior due to applied temperatures and in the various heating and cooling scenarios. Researchers have observed significant increment in thermally induced crack density after 600 degrees. The main reason suggested is alpha to beta transition of quartz and many other mechanisms. So here, this tested granite had over 50% of quartz, and we can clearly see beyond 600 degrees significant thermal damage. We further observed this with microscale observations. This study, we looked at effect of thermal cycles, cyclic heating and quenching, which is very common in geothermal reservoirs. And again, you can see the strain distribution during the failure. So below 300 degrees with minimal heating and cooling cycles, we can see predominantly a shear-dominated, relatively simpler fracture planes, but with increase of heating and cooling cycles as well as target temperature, we can see quite complex fracture planes, especially you can see beyond 500 degrees. And here you can see the effect of temperature and the cyclic quenching impact on mechanical properties, again showing a significant reduction of strength and in the stiffness of the rock, as well as higher deformation and lesser brittleness at higher temperatures and heating and cooling cycles. We also used acoustic emission detection technology to study crack propagation in high temperature conditions when they are subjected to shearing. We know when brittle material is under stress, strain energy is released during the development of new cracks or widening of existing cracks. We can capture this energy using acoustic emission technology. Researchers have divided the crack formation into different stages, like crack closure, crack initiation, secondary cracking, crack damage, etc. So here you can see stress strain curve as well as cumulative acoustic energy count plots. And here we have defined 3 different stages. So initial crack closure, here most pre-existing cracks are first closed, releasing quite insignificant number of acoustic signals. And then here you can see stable crack propagation region. where gradual linear increment of acoustic energy, and then finally unstable crack propagation region, where we can see exponential increase of acoustic emission energy. Then based on these stages, we defined stress thresholds, and here you can see stress threshold we considered in this study. And these are the experimental results for tests conducted under different temperatures and different cooling scenarios. So acoustic emission analysis further explained thermally induced damage due to heating and then cooling. With increased temperature, elastic region as well as stable crack propagation region is decreased, and unstable crack propagation region is increased, and cooling can further accelerate these mechanisms. And these are some examples when it comes to cyclic heating and cooling situations. And this data indicates decrease again of stable crack propagation and increase of unstable crack propagation with the increased quenching cycles. To further understand this thermal damage and quantify it, then we use temperature-dependent Young's modulus and temperature-dependent uniaxial compressive strength as key indicators. And one thing we found is up to 600 degrees, this relationship with temperature and thermal damage is quite linear, but beyond 600 degrees, it was non-linear, indicating the necessity for advanced models to accurately capture these damage mechanisms. Given today's focus is on integrating microstructural analysis on geothermal geomechanics, next I will move to microcracking mechanisms triggered by this thermal loading. So among different microscale techniques, computer tomography or CT imaging has evolved to quantify pores and microfractures, providing digitization of this internal structure. And by examining micro-CT, we could observe substantial matrix degradation in reservoir rocks caused by thermally induced microcracking. So as last presentation also discussed, in crystalline rocks like granite, we can identify different modes of cracking. So here we mainly captured two modes of cracking: intergranular cracking, cracks propagate along the grade boundary, and intragranular cracking, where cracks propagate through the grain boundary, especially weaker minerals, as you can see here. And results show that propagation of cracks through grain boundaries increase significantly with the increase of preheating temperature because of the thermal stresses and then the natural anisotropic nature of rocks. Rock is consists of different minerals with different thermal expansion coefficients and different thermoelastic moduli causing this anisotropy. And once thermal stress exceeds the internal strength of the rock, fractures are initiated through this weaker planes, which could be pre-existing grain boundaries or weaker minerals. And we studied again different types of rocks to understand the effect of mineralogy. And we quantified the distribution of those cracks, types of cracks, etc. And these are some more work with high resolution CT images, which then used to develop reconstructed 3D structure. And here we identified different minerals and cracks, as you can see here, by considering the contrast and then the brightness of the CT images. And then we used multi-thresholding segmentation techniques to separate different minerals, pores and fractures to detailedly understand the microstructure. And this is the algorithm we used. I'll talk a bit more about this process and pore network modeling in the coming slides. Crack quantification involves again determining total porosity and connected porosity. We found the total porosity using segmentation of these 2D images into cracks and minerals. Next, by removing isolated pores, we can obtain the connected porosity, because connected porosity is the important parameter when it comes to fluid flow through fractures. And these are the distribution of total and connected porosity along the length of the sample and along the width of the sample. And this plot shows average porosity, because you can see porosity varies with the length of the sample as well as the diameter. And you can see those average values for different temperatures as well as different cooling conditions. As expected, rapid cooling had a greater impact when it comes to micro scale damages. Next, we could generate pore network models, which helps us to understand the size and distribution of pores and then the throats. So here you can see the meaning of a pore network model. Basically, we understand pores and then the connectivity of those pores using throats. And then we can understand the coordination number, which helps us to understand the connectivity. These types of simulations helps us to calculate the length, areas, diameters of pores and throats. And here you can see those generated models for different temperatures and cooling conditions. These are the results for cyclic cooling, cyclic quenching scenarios. For this considered resolution, which was 10 microns in our facility, we could not generate pore network beyond 500 degrees. So that's another challenge with these types of microscale analysis, the challenges associated with the resolution and then the size of data. Again, another thing we found that increasing quenching cycles cause substantial damage, even more damage than single ones quenching cycle with quite higher temperature. And we found large pores appear near the sample's boundary, where we get the highest thermal gradient, and then tiny pores expanding internally. The permeability of the granite samples are then simulated using these pore network models, considering fluid flow streamlines between connected pores. And here you can see the results, which shows the impact of increasing of temperature as well as quenching cycles. For example, the permeability was 7.6 Darcy for 500 degrees 5 quenching cycles. It increased to 12.4 Darcy with 15 cycles. And you can see it's even higher when it comes to 900 degrees 1 quenching cycle, etc. We verified these simulation results by conducting laboratory experiments. And here you can see those experimental data. So this is one selected sample as 600 degrees 1 quenching cycle. And we found a linear increment of pressure gradient, showcasing the steady state behavior and applicability to Darcy equation in this scenario. However, with the increase of confining pressure, you can see permeability is non-linearly decreasing in this scenario, showing the impact of confinement for these generated fractures. And we found the simulated results and then the experimental results are in the same order of magnitude. Next, I would like to move into the next topic, hydraulic fracturing of granite rocks under geothermal conditions and use of microstructure analysis in that area. Hydraulic fracturing in geothermal reservoirs has always been challenging because of complex stress conditions, high temperatures, presence of faults, fractures, fluid losses, and many more. There are 4 laboratory scale experimental results can provide valuable information in fracture propagation compared to complexities in the field scenarios. So these are some of the experimental work we conducted under different confining pressures as well as temperatures. One thing I want to emphasize is the stress rate is very important when it comes to fracture propagation. And therefore, we carefully control the axial load and then the confining pressure during these experiments to make sure we get a vertical fracture like this along the axis of the sample. And in order to simulate the well bore, we drill the sample centers up to mid-depth employing a 3 millimeter drill bit. And this is a typical injection pressure versus time curve or breakdown pressure curve. And we found breakdown pressure is linearly increasing with confining pressure and linearly decreasing with the temperature. And also the rate of breakdown pressure decreased with the increase of pressure. And in this study, we also developed modified breakdown pressure criteria incorporating temperature-dependent parameters of the reservoir rocks. Another work I could contribute is use of different types of fracturing fluids other than water. So here you can see results of water and then supercritical carbon dioxide and CO2-4. So carbon dioxide changed its physical state from a gas to a supercritical liquid in high pressure and high temperature scenarios. And when it comes to carbon dioxide-based fracturing fluids, this phase transition is a very important consideration. So we need to carefully control temperature and pressure and monitor rheological parameters like viscosity, compressibility to ensure the fluid is in the correct scenario. And here you can see this breakdown pressure curve. We can see a linear breakdown pressure, linear pressurization in the well bore, and compressibility of the stimulation fluid govern this well bore pressurization rate, and water being the highest and the supercritical CO2 being the lowest. So we observed that in this data. And fracture initiation or the breakdown was identified like sudden drop, as you can see here in this breakdown pressure curves. Another thing is post-breakdown scenarios and how different fluids impact post-breakdown. So here you can see developed modified breakdown pressure criteria incorporating fluid flow pressure and thermoelastic effects. One thing I want to highlight is the type of fracturing fluid and in situ stresses and temperature are very important factors when it comes to fracture propagation and development of secondary cracks, which I will introduce briefly next. And these are some results again from CT scanning of these hydraulically fractured samples. So according to the results, we can see based on these images, fracture tend to propagate along grain boundaries. However, while they propagate continuous, they tend to break weaker minerals in the flow path. And under confining pressures like this, so these are under 20 megapascal confining pressure, you can see closure of fractures and grain crushing with confined scenarios. When it comes to high temperature, this means rock is at heated scenario, in this case 300 degrees, and we inject cold water. We can observe some thermally induced fracture zone close to the well bore, but you can see the thermally induced fractures are extremely small because the resolution of these images are 10 microns. And these are some more data, especially related to supercritical carbon dioxide fracturing. And you can see tensile fractures are induced close to the wellbore. And you can see in some scenarios diametrical fracture, and then some we can see secondary branches. Especially we observe this feature with carbon dioxide, and at quite higher temperatures like 200 or 300 degrees, fracture did not propagate full length. Instead, microfractures were detected to the outer circumferential periphery because it at these conditions, as a result of thermally induced fractures, it caused leakage of CO2 to the membrane, and it caused very small microfractures, which we could not capture in CT. But we certainly observed outflow, but we could not see the large fractures visible with CD. We found temperature significantly affect the morphology and induced fractures. And here you can see how fracture density, fracture tortuosity changes. For example, here you can see at 50 degrees and 100 degrees change of fracture density. These observations support that under high temperature conditions, CO2 has the potential to percolate into thermally induced tiny microcracks, propagating existing cracks. And another thing we observed in this test was compared to water fracturing, complex fracture patterns, multiple fractures are developed with CO2. These microscale observations helps us to understand the flow behavior of these induced fractures. So we did laboratory experiments with fractured samples to understand the permeability. So as I mentioned last time, confining pressure has a significant impact, and you can see nonlinear reduction of permeability or closure of the fractures with induced confining pressures. Another finding is carbon dioxide-induced fractures more than 3 orders higher than that of water-induced fractures that we observed with micro-CT images. My recent work looks at nanoparticle enhanced foam-based fracturing fluids to enhance fracture conductivity, because CO2 has some challenges when it comes to hydraulic fracturing, like very less propellant carrying capacity. Therefore, incorporating CO2 foam can reduce that kind of challenges. And another area I'm working is stress corrosion fracture growth due to rock fluid interactions using micro-CT. Yeah, considering the time limit, I conclude my presentation here. So today I presented some selected research relevant to thermal damage and fluid-induced fractures with focus on microstructural analysis in geothermal geomechanics. So overall, thermally induced microcracking and core expansion play a very important role in damaging rocks in geothermal environments, affecting fluid flow and fracture behavior. The choice of fracturing fluid like water, carbon dioxide, or foam can significantly impact how fractures form, and especially foam and CO2 offer benefits in reducing water use and creating more complex fracture networks in low permeability rocks. We have very limited understanding of complex mechanism associated with geothermal applications. So fundamental research in geomechanics is very important in these types of new directions, because essentially geothermal energy related work require a lot of work when it comes to characterizing the reservoir and then creating the fracture network and then operation. All these require a lot of understanding of geomechanics research. That's all. Thank you very much for your attention. The material I presented today is a collaborative research effort. So therefore, I want to thank my mentors, my collaborators, my students, and support from Monash University and University of Wollongong. And thank you very much for this opportunity. This special rock triaxial system had limitations when it comes to sample size. So our sample height was 45 millimeters. So the length of the borehole is half of it, 22.5 millimeters. This is probably an unanswered question in geothermal geomechanics discipline because I visited one petroleum hydraulic fracking field and when I discussed with the challenges with the field engineers, we basically understand the fracture propagation through fluid losses and change of pressure. There is no way you can take images during the field scenario under this deep geological conditions. So I think my work mainly tried to understand why and how these fractures propagate and the impact of different types of fluids and temperature, that sort of scientific understanding. But having said that, to explain this in the field scenario, we need a lot of future work. I know some researchers are working with the industry using laser, maybe optical fiber, that type of technologies to find that relationship, that link with laboratory studies and the field scenario, especially in the petroleum environment. But when it comes to geothermal, temperature is a big challenge to create sensors that work under these types of pressures, temperatures, that lot of things needs to be done in this area. Yes, that's so I did mechanical tests under in situ heated condition without cooling. So, but again, those types of experiments require custom built equipment. So you can't simply buy that type of equipment. So I was very fortunate to use that kind of facilities. But all the CT work or even scanning microscopy, they are for the cooled samples. But having said that, systems are developing to operate under relatively lower temperatures, let's say less than 100 degrees. But still, I'm not aware of a facility which can produce in situ temperature. I know there are facilities available with in situ stress. So you can apply this stress and then you can do the scanning, that type of thing. But we need to develop this kind of new systems in order to that kind of very innovative type of tests. But having said that, mechanical test shows even heating cause damage, but heating following cooling produce more damage. And if you have a higher cooling rates, damage would be even higher. So I could capture those scenarios with mechanical tests. Based on the mechanical experiments, based on by looking at the uniaxial compressive strength or stiffness or brittleness, we can assume there would be less thermal damage under heated condition without any cooling. But I don't have any experimental evidences. That's true. Granite is quite chemically resistant, strong, brittle rock. But when it comes to carbon dioxide, the viscosity is low compared to water. So it allows to propagate through microfractures. We believe that's the reason why CO2 induced fractures, although they are microfractures. I mean, you can very clearly see water induced fractures, but that's only one major fracture. When it comes to carbon dioxide, there are multiple fractures. Although fracture aperture is small, because of the ability to percolate through the microfractures with very low viscosity, I think that's why permeability is high in CO2 fractures, fractures caused by carbon dioxide.